Yeah, so I'm going to talk about shape optimization discrete surfaces. And as you remember, maybe in November, I gave a first talk about my thesis, or work done in my thesis, which was concerned with shape spaces and especially the space of discrete shells. We talked about some representation of the space, we talked about some data-driven constructions, and we didn't really talk about this last part, but yes, we'll also not talk about this today. So today we focus on the second part of my thesis, which was about shape optimization, which of course is a very loose term, but here it's mostly XPD constraint shape optimization. And we're actually going to see two projects. One is about stochastic bilevel shape optimization. So this is like nice geometric things over here. And then we're going to talk about some phase field approach to surface segmentation, which is these nice spheres in the bottom. And we're actually going to begin with this stochastic bilevel optimization part. But before I get there, I want to recall some things about discrete surfaces and discrete shells. So what do I mean by discrete surface? So essentially, it's a fancy way to say it's a triangle mesh. But it's a triangle mesh that fulfills some requirements on the regularity of the surface described. So it should be a manifold actually, and so on. And furthermore, typically we assume that we have one fixed mesh, but we change the embedding of this mesh, right? So the connectivity is fixed, the amount of vertices is fixed, the triangles are fixed. You just change the position of the triangles in ambient space. And we can see this as a pairwise affine immersion of this topological space given by the triangle mesh, or equivalently just by describing the nodal positions as a vector in the dimensional vertex positions. And then if we come to discrete shells, so shells is a physical term for like thin bending object. And what we want to do is we want to use some kind of discrete shells energy, which means we want to have an elastic energy that describes sort of the difference or the amount of energy you need to go from one configuration to another configuration. So two different sets of immersions of the same triangle mesh. And you want to have some measure that sort of describes the difference between the two, describes them in terms of like a physical-based way. So you have your model that has two components, which is called a membrane component, which is basically in-plane stretching or a distortion of your surface. And then you have another part, it's a bending energy. Well, it does what the name says, it measures the bending of your surface. And sort of these two contributions are weighted by this delta or delta to the power 3, and this delta is sort of a small thickness of your object, right? So if you think about, for example, a sheet of paper, it has a finite, a very small thickness, and this would be this delta. And as you can see, it sort of has different scalings, like membrane scales linearly, and then the bending part scales to the power of 3 in sort of things. This also describes sort of the thicker objects. Then, for example, bending becomes much more expensive, which is something you can also experience in real life. But if you relative to membrane distortions, but if it's very thin, then bending becomes very cheap.
Joshua?
Yes.
What is the difference of factor? Delta 1, delta 3?
Okay, so
Intuitive explanation.
okay, so the true explanation is that these are different. So that actually, to get these kind of models, what you would do is, for example, to get the bending model, you would assume that it's basically asymmetric deformations. Then you look at like thin objects, like thin 3D objects, and you can talk about limits of like having a thickness go to infinity, and look at the gamma limits of like three-dimensional elastic energies. And in the right scaling regimes, either like membrane or bending energy pops up. And an intuitive explanation is just that sort of, okay, if you make your object thinner and thinner, then basically what you expect is that bending comes as cheaper because this power of 3, right? So if I take a sheet of paper, it's very easy to like you can deform it membrane. I can have some membrane deformations, like in-plane distortions, but they will be very small. But because it's very thin, it's easy to bend a sheet of paper. And something similar applies if you think about, for example, like if you have metal, if you think of some piece of aluminum, like very like if you have it in your kitchen, it's like very easy to bend, it's like very easy to crumble. But it's very relatively stiff to like membrane deformations because it will tear basically. So it won't deform elastically anymore, but it will just tear. But if you have like a thicker sheet of aluminum, you can actually like distort it in plane, but it's much harder to bend. Sort of why expect this regime not delta and delta to the power of 2 when this pops up, as I said in this analysis. These are just exactly correct scaling regimes. And I guess you can also measure them if you're in a physics lab, but I don't know. Right, and then it's okay, as I said, membrane have these in-plane distortions, and what it does is it measures the change of metric on a surface, where metric in our discrete sense case is just giving like piecewise constant by the derivative of the immersion squared. And then there's the strain tensor, which tells you, okay, for two different embeddings, how much does my metric change per triangle? And then I integrate this energy density over this change of metrics, over the strain tensor, on which this particular energy density, which is called a neo-Hookean model, just a particular description of how your object changes. Basically, it tells you has three major components. So this trace part measures locally the change of length on these surfaces, the change of the length element. The determinant measures locally the change of the area element. And the logarithm of determinant basically gives you interpretation avoidance, because it tells you that your determinant cannot go to zero, so you cannot compress your object to infinity. So there's some limit on how much can you compress it. And compressing is at a certain regime is much cheaper than extending it.
So I think I asked you the question back in your first presentation, but here, because there's no equation saying A is equal to something, but so identity corresponds to A equals identity, or A corresponds to
okay, so identity, okay. Basically, so A is the change of metrics, how much metric changes. And yes, identity would be the metric stays the same. And then, of course, identity would be, so this energy is zero for identity. Can you compute this? Also, derivative is zero, so it's a global minimum. It's local and also global. And this thing is positive definite at this point also. The hashing of it. And yes, so basically, yes, what this energy says, this energy would be happy if your change of metrics identity everywhere, then it's zero. And then otherwise it sort of measures the change of this, the derivative, the distance to this. And then the other part is the bending energy. So you want to measure bending on discrete surfaces. And this is really a discrete thing. So I mean, for this one, this really looks like, okay, you integrate something like that's actually a continuous object, this membrane energy, and then you basically have a discrete integral over triangles. And this bending energy is a bit different because you really have now a discrete quantity, which is the dihedral angle. So it is the angle between two neighboring triangles. And it has a sign, and this is important. So it's a signed angle between neighboring triangles. But this sign is given basically by the direction of edges. So we also always assume that our triangle meshes are oriented. So we know have a consistent orientation for our triangles. And then you can just measure the change of this angle for every edge. And then we have some weights that basically have some area and length elements localized to this edge, which basically gives you some kind of consistent integration constants, so that if you basically combine these two things with this weighting of delta to the power 3, you actually get the same physical units if you spell this out in the end. And this sort of works out. But let me stress maybe, so yes, there's some membrane energy, of course, as I said, it looks like very basic discretization, so here converges is not a big question, but for bending energy, it's a question if this actually converts to a continuous bending energy. And the answer is basically yes, if your mesh is good enough. So if you have a Delaunay mesh, then it will converge. But having a Delaunay mesh is a very big ask in reality. So it's a bit questionable, especially if the coarse meshes. And of course, you will have some discretization artifacts because it can only bend at edges, and so maybe it's not the right thing. So if you have, for example, a lot of edges directed in one direction, then you will have some bias into which direction it can bend. But yes, so if you have nice meshes, you can get convergence, and also if you can, there's some modifications of it that actually give you convergence, also not so nice meshes.
Maybe something we should add on the energy density is that in fact this is the energy density for the measure on the extilde surface element. Because to get the energy you have to integrate on something.
Yeah, but but it's the integration on X. It's the integration on the undeformed. You always integrate on the undeformed.
Yeah, but you have. I think so my question is that's the question. See, this is the energy density, so you have to integrate with respect to.
Yes, but so you have.
Yes, you integrate on the X, but you are doing change variable. You have volume. You have a Jacobi, which is somewhere, or you have to compute the area of a triangle after the deformation.
No, before triangle, before deformation. Okay, yes, there is a change of variable in here. You could also write this as integral over the deformed configuration, but we typically write it as an integral over the undeformed configuration. Because also, maybe I have to go a step back. So this formulation of having two embeddings as inputs to an elastic energy is a bit non-standard. Because normally what you would do in elasticity is you have an object, a reference object, and then you have deformation acting on it, right? And then you would say, okay, what's the energy of this deformation? But here in this discrete case, we know if you have two different emergence, I know the deformation because it's two triangle meshes with the same conductivity, so it's given, so it's fixed, right? So
Yes, with respect to the reference.
Yes.
Shape.
And so typically, this could be, you could also say, okay, this is the energy of the difference between these two with respect to some reference configuration, which is given by this X itself, and then you would integrate over this reference configuration. Yeah, well, maybe that's a good thing to say. It's a bit non-standard for elasticity, but it's just like a benefit or side effect of this discretization kind of thing. Okay, and this basically gives us the intro to our first bigger part. So this is stochastic bilevel shape optimization. This is a collaboration with Johanna Burtscheid, Matthias Klaus, and Rüdiger Schulz from the University of Duisburg-Essen. They're experts on like optimization and experts on economic optimization, these kind of things, like bilevel optimization, as you're going to see in a second. And then also with my PhD advisor Martin Rumpf and Sergio Conti, who are both from Bonn, as I used to be. And so the question we asked ourselves in this project is basically it's a continuation of a long time collaboration between these groups in Bonn and Essen, and all of the thing has always been to ask like, okay, there's like certain types of optimization that are heavily used in economics or economic-driven decision theory, whatever, and can we apply these kind of optimization techniques also like to elastic shape optimization problems to be able to model some new phenomena or something. And concretely here, we looked at something that's called bilevel optimization, where you have envision multiple actors in a system, like you have what's called a leader, or in this case already bilevel shape, stochastic shape optimization. So we have a leader who makes a decision. Let's say it could be a policymaker, for example, like the government creates a law. And then there's followers in the system, like let's say citizens that have to abide to this law, but make their own decisions, how to optimize their own, what they want to do, like maximize their profits, let's say. And then but actually it's sort of the leader that creates the law has some overarching goal it wants to achieve. Let's say if we want to create markets to decrease like carbon emissions and so on, and then you have people like acting in these markets, like making decisions to save money. And so then the question is for a leader, how do I have to design my market or my laws such that in the end, the outcome of doing some model for what the follower is doing, gives me my desired outcome. And typically there's some like randomness in these models because there's some things you cannot completely model. So it's just like there's some randomness going on, sort of perturbs the decision of the leader when it comes to the follower. And then the question is, okay, how can we take this and actually do something? Is there like a model in elastic shape optimization where this would make sense to apply? So can we give this some meaning? And so now the model changes a bit to what I told you before because, okay, we want to do elastic shape optimization. So what is elasticity here? And you have to simplify a bit because we added a lot of complexity on a set of optimization on this like bilevel approach. So we have to dial back a bit on the elasticity that we're doing. And also we have to introduce what are actually design variables. And design variables are going to be, in this certain scenario, the thickness of my object. So I say I have a fixed geometry. Let's say I have a fixed surface like this gray thing on the bottom here, which is some architectural model. And I can sort of design, and this is made up of triangle panels. So like you have a triangle surface, and I actually envision this now as a design choice of an architect. He might build an object out of triangle panels, glass or plastic, whatever. And then I can decide how thick should these panels be, right? And that's the question, how do I design them optimally, optimal thickness, right? And they could be uniform, but maybe that's not the best choice, depending on what my load scenario will. And so this maybe sort of changes our energy a bit. So now we have an elastic energy, and now this rotation is not completely perfect compared to the previous slide. So now U and Y are not two different configurations. But as I told you before, now U is my thickness, my design variable that I can change. And Y is the displacement that I have. So it's from before, it's like the difference, like it's X minus X tilde. No, X tilde minus X. It doesn't matter. And give my energy information, then like the variational formulation of such an object deforming is just having the elastic energy for its displacement minus sort of if you have forces acting on it, which is F, so I have some kind of external force acting on my object, pressing on it, like gravity, like wind, whatever. And then this is basically a variational formulation telling me how to compute the resulting displacement from such an external force acting on my elastic object. And this is basically where elasticity comes from. So this is a discrete formulation of like the essential basic, the central equation or essential variational formulation of elasticity or hyperelasticity. And So as before, we have now these bending and membrane energy, and now it's a bit different because previously I said, okay, we have these delta parameters, right? And these delta parameters are something like thickness, but they were constant. They were just like, okay, I have one my surface, has one thickness, and done. But now I want to vary them over my surface. I want to vary the thickness of different triangle panels, and then this basically changes my energy in a sense that, okay, my membrane energy, you have per triangle, you have a thickness. So this just goes in there like where the delta was before. So linearly changes my amount of energy I pay. And then for bending, we have a cube. But as I said, I have thicknesses per triangle. So what's the thickness of an edge? Okay, here we just make a simplifying assumption, say it's just the average, 2. And then this is to the power 3. So if I change the thickness per triangle, it changes cubically how much bending energy I pay for the adjacent edge. Okay, now I said I have to simple.
UT prime is what?
Okay, so yes. So I have an edge, and edge has 2 neighbors, T and T prime. And then UT is the thickness of one neighbor and UT prime of the other neighbor.
Okay.
Okay, now I said, okay, this is still complicated, it's still nonlinear because this W is still nonlinear, the same thing as before. I just hidden, like, for example, the bending stuff in, like, calling it bending. So we have to simplify, as I said, and for this, we linearize our model. Yes?
I'm sorry, I didn't follow. What is your data and what is your goal?
Okay, so I said my design variable, what I can change about my object, my geometric object, what I want to optimize is the thickness. And the thickness is called U, and this per triangle thickness. And then what will happen, and then what there's some force acting on my object, because it's an elastic object, I press on it, whatever. And then I want to, in the end, control some of the displacement, right? My object should not move too much.
So you have Y, which is your object,
the
position of your node.
Yeah, not directly, it's a change of position in this sense. So I have a fixed given reference configuration in this sense, this X, and then this Y is the displacement. So how much do my works positions change?
As optimal of an energy, or?
Yes. So it's basically defined. It will be defined by this.
Yes,
so
okay, you want to find Y minimizing this.
Yes.
And you want this minimization
so
to
this
be close to an observation? Or?
We'll come to what it actually should be in the end, we'll see in a second. How we control this, because this will be a bit more complicated. But okay, so typically you can imagine as the typical goal in elastic shape theory is that the Y should be small. Because Y is how much my object is moving, and I don't want my object to move. So if I'm under a roof, it should stay in place. It should not go down. Otherwise, it would have a problem. So the basic goal is always the Y should be small. What exactly this means is we'll see in a second.
Okay.
And sort of Y comes from, okay, Y depends now on my pure parameters, and Y depends on the forces acting on my object. So how much is there pressure is on it.
Okay, so here you suppose that you know your thickness U.
Yes.
And you need that partial. Okay, and the simulation of the definition. Okay, thank you.
Yes.
Sorry, just also on the same thing. So what's the intuition about this minimum over Y? So you want, the solution of your mechanical problem is so the displacement is given as the minimum of the bending energy. No, the total elastic energy plus what?
Plus, okay, so I have force acting it, and this force times M is the M is the mass matrix, just from finite elements, and Y is displacement, so it just tells you how much it's following your forces.
Okay.
And if, for example, if I press on something and there's no resistance, this thing will just go to infinity and it just go like further and further. And sort of this W measures the internal resistance of your object to change.
Oh yeah, because okay. So it's not the elastic energy of the system; it's the elastic energy related to the displacement.
Yes.
So maybe that's.
Yes. So if I have some displacement of my object, I pay for it like to some internal friction. Yes.
Okay, so.
Right. Okay. And then sort of I say I want to simplify the model, and a typical way to simplify it is to linearize it. Where actually in this case, like linearization is just, okay, we do a second order Taylor expansion around 0 or an identity, because identity is, like, as I said, a minimum. Like the first 2 terms go away, and we just have the second order term. Okay, there's some bracket that shouldn't be there. And then basically we get this sort of like this linearized energy is just quadratic, and with the system matrix basically Hessian of your elastic energy from before. And then you can, okay, plug this in as a replacement for your energy in this elastic problem. And then it's not just a quadratic problem, and you can write down the solution, right? The solution is not just a linear system. And this is basically a multi-dimensional version of Hooke's law. Maybe you remember Hooke's law, basically, because you have a spring. It's sort of the force of the spring acting against it is proportional to displacement. And this is just the same thing. So I have a displacement, I have a force acting on it, and just tells me, okay, my displacement is proportional to my force with some like portion factors, which is like a linear mapping in 3D. So this is basically the important thing to remember for our rest. Elasticity in this first part is just, okay, it's Hooke's law. We have some system matrix, which depends on my thickness, my design parameters, and it relates my displacement to my forces.
Okay, and just a question is that probably in real life, when you increase the thickness, then the forces also change.
Yes.
So that would make the problem more difficult.
Yes, okay, yeah, because, okay, if you think about gravity and so on, then yes, your force will also change. In our model, this is not so important because you can already see this, sort of the assumptions we make on a reality here are not really realistic. So sort of the scale of things is a bit off. And bit off, I mean, okay, maybe I tell you this when you see the example, I tell you what actually the measurements are that you would have in reality to get this kind of behavior. And yes, okay, as I said before, there's some underlying continuum model that we talked about before. Yes. Okay, now let's talk about stochastic bilevel optimization some more. And I basically already explained this. So what happens in stochastic bilevel optimization in general is you have a leader, and this leader makes some decision U, which is in our case just a vector of values per triangle. Then there will be some like stochastic perturbation of this U, and this will be just some point-wise perturbation. Then the follower gets this decision as input, and they make a decision. In our sense, we say, okay, they make a relational decision, so they maximize some objective. They want to maximize their profit, or we're going to see in a second what they're going to do in our case. And so they have this U as input, but they get actually the realized U. So they get the U that's perturbed by some stochastic noise. And then they make a decision, which is F in this case. And sort of the name already gives you a hint what it will be in a second. And then sort of the output of the decision goes back to the leader. And now they can optimize like the whole thing. They optimize the decision such that the outcome of the follower sort of minimizes what their cost function. So they have a cost function of J, which is a different one in general, also depending on this U and this F. And okay, maybe the decision of the follower might not be unique, right? So there might be multiple like solutions to this problem. And so the solution thing here is a set, not a single decision. And then in our case, we use something that's called pessimistic bilevel optimization, where basically the leader assumes the worst case scenario, so the worst case solution of the follower, which of course is in many scenarios more realistic, but also much harder to analyze. And then of course, okay, there's some randomness, and the leader hedges against this randomness here and just by expected value to integrate this. And okay, now how do we apply this to shape optimization? So what we think of this leader, we think about some design engineer. So this design engineer designs your object, and they have to choose the thickness of your triangle. Right, so these are not just some pretend roles in this scenario. And then, okay, what's randomness? Okay, randomness enters from manufacturing errors, right? So someone actually has to make these panels and has to manufacture them. And of course, they're not manufactured perfectly. Depending on where you make them, they're more accurate or less accurate. And so what we say, okay, basically you have just per panel per triangle, we have a point-wise perturbation of the thickness by some truncated normal distribution. It could also be a normal distribution, but for the analysis, if you want to show something like existence of solutions, you need a compact support distribution. Maybe you don't need it, but the proof that we have needs it. Yes, you have a point-wise perturbation by truncated normal distribution. And then the test engineer wants to break the object. So the follower is a test engineer. So some guy in Germany from the TÜV that tells you, okay, now you have built an object, now we're going to test if it actually holds up. So I don't know, like a crash test for a car or for a building, there's people that just, they get the building plans and then tell you in the end, is this building sound or not? Can you actually build this? And is it safe? And this test engineer basically looks, okay, well, how can I break this object? What's sort of the worst case scenario that can design that has the most effect on this object? And here we use something that's called compliance. is basically the size of the displacement, but in the norm of using this h. If you think back to 4, it's actually the same thing because there's just a mapping between j and so there's a relation between this.
So this is the energy. This is the
Yes.
elastic energy for the
Yeah. So this
under the forces.
yes, this is basically the elastic and
try
sense.
to
Yes. It's how much. It's
maximize this.
yeah, it's called compliance. It's the same in the linear case. It's the same thing as how much it follows your forces, like how much is it acting to the force I'm putting on there, and how much do I pay internally for the elastic energy. And this basically, the test engineer wants to just maximize this. He doesn't care where it happens. He just wants to maximize this. And of course, here we have this J, which depends on U and F, and this is where physics enters to this elasticity. So we use what we've seen before. So it's given by this H of U inverse times M times F. So just basically solving a linear system, so that's a linear relation between displacement forces. And basically this enters here as you could say a third level problem, but because it has a unique solution, we don't really consider it as a level. Okay, now the test engineer has made their decision on what kind of forces breaks the object, and then sort of the design engineer in the loop decides, okay, now I have to actually decide what kind of material distribution will I choose, and has some other cost function that depends on this. And we will make these cost functions a bit more concrete for the design engineer in the leader, and design engineer in the following. So it's this basic concept clear. So you have basically two, you can imagine as people. One is building the object and then knows, okay, another person will try to break this object. So he tries to anticipate the choices, and he also knows there is some manufacturing error that will occur after I design my object. And then he tries to find a design, but design here means just how thick is my object that sort of maximizes and minimizes some cost, which will also be related to how much it moves, but also to actually cost of manufacturing, for example. Because I could just make my objects infinitely big. It's a solution. Sure.
So when you said that psi u is a set,
yes,
it's only in very special cases. I guess in general it's just one value. This is Armax.
Okay, so no. Actually, this can become a set quite easily because, for example, as soon as your object is symmetric, let's say if some rotation symmetric, I can just I don't know, maybe I have some, and my force is sort of follows this, and my material distribution also symmetric, then just basically there's always infinitely many solutions.
Okay. But it happens also quite often that it's just a single value.
Yes, for example, for example, if there's something that breaks symmetry, which we'll see in a second, then yes, it becomes just 1 point. And okay, so maybe this is also we talk about this.
But still J represents a max, okay, because it's okay.
Yes.
Okay, and just because, a few slides ago, when you presented the problem as what is the thickness that I should choose to minimize y, basically I said, okay, then put just thickness everywhere. Certainly it's going to be very stiff.
Yes.
But here, if I understand correctly, this is more or less normalized like
Okay,
this,
yes.
because actually if you increase the thickness, then you increase the energy, and then...
Let me tell you. Okay, so this perfect segue into the next slide. So what's actually the cost that I have to pay? What actually is the cost of my leader? Why is not just make everything as thick as possible the solution that I want? And so, okay, so first, there's multiple ingredients that go into the cost of the folders. First, there's also some cost of my object shouldn't move. And this could be it shouldn't move anywhere. But for example, it could also be something like a tracking cost where I say, okay, I have a certain region on my object that should not move. I don't care so much about the rest. This can wobble around, but this in the middle has to stay fixed. For example, here in this kind of simple convection, we'll see this set. We just track the top of the object, and they say the leader only cares about the top of this object. The arms here are made to have some kind of wobbliness. They're made to move around, but this in the top state should stay fixed. And this is basically just measuring, okay, how much displacement is there per each of these points and summing this up. And then I have some restrictions on what I can actually make with my material. So I have a minimal thickness for each panel, because there's something, okay, below this, I can't manufacture it. There's also an upper limit, tells me, okay, I can only go to this limit by manufacturing or whatever. And then there is a limit on the total amount of material I can use. And then, of course, this basic constraints make you have to distribute your material somewhat cleverly. Of course, only if sort of like choosing the maximum U plus everywhere is not feasible in terms of the V plus, right? Because if this would be possible in my solution set, then of course, yes, everything would have the same thickness to maximum 1. Okay, done. But we assume in the case where this is not possible. And then also you make another simplifying assumptions on the forces that can actually be applied by the test engineer. We say the test engineer can also use some kind of realistic scenarios. So let's say this is a building, there's, I don't know, we just take like wind forces in like 2 directions. And these are like very simplified wind forces. This is not a fluid structure interaction model or anything. It's just like a force going in this direction proportional to how much the triangle is oriented in this direction. Very, very simple. And then the other direction. And then there's a third force, which is basically gravity or like overlay, like snow on your roof. So if you maybe build somewhere where there's snow and or like rain and water on your roof or something like this. And basically then we have 2 constraints. These forces can also not be arbitrarily big, because then it would also be a solution for the fall. We could just make them infinitely big and they win. And so there's 2 limits. So there's a joint constraint on the wind forces. So there's a total amount of wind that you can get. And then there's a separate constraint on the amount of overlay you can have on your roof, how much that can be. And then also this has 2 effects. The first makes it realistic, but also in this case, we assume a linear combination of these kind of forces. So actually we just optimize forces in a 3-dimensional space. So the follow-up problem gets much easier, because you have to imagine you optimize the leader problem, then in each iteration of the leader problem, if you do some descent algorithm, we have to also multiple times solve the follower problem. So the follower problem needs to be cheap for this to be feasible. So this is why we restrict to like a smaller dimensional set of forces, which also has some interpretation. But SK, maybe again, this is a mathematical problem. This is more like a proof of concept kind of problem for this approach of applying it to elastic shape optimization.
Okay, and why, because, okay, I understand that the shape of your constraints depends on what you have in mind, but why did you decide to depict it as a cylinder? It looks instead of a cone intersected with a ball or something.
Okay, so it's a cylinder because it's basically what it is. So I have a constraint that on the first 2 ones, on B1 and B2, that the norm of these 2, like sum of these 2, the norm is constrained, right? So, and this is basically a circle on my first 2 coordinates, and then my third 2 coordinate can just be up to a certain limit. They should also maybe be related, of course, like if I have like a lot of wind, I would have snow on my roof, okay, given that, but yes, it's just easier to not couple them more. This is why this is a cylinder and not a cone, for example.
So to be sure, what FUF is the displacement for the? Oh no.
It's displacement of the.
No, so I'm okay. That's not clear to me to make the connection with the psi. Psi is the worst.
So psi.
The elastic energy in the worst case under.
Okay, so psi of u is the worst case force, or the set of worst possible scenario forces chosen by the follower, like the forces that create the maximum of elastic deformation. And y of u of f is the specific displacement for like one set of parameter material and one set of forces. And so in the leader case, this f will always be an element of this. So if you assume it to be unique, then of course it will just be psi of u.
Okay. You can use the blackboard if you want. Because they have just to write all the definition.
So, no, but we see more about this. So because now we have to talk about how to make this practice. So it comes back now.
Okay.
Because as I said, for example, psi is something, it's a set valued thing. I do not want to complete this whole set valued thing, like all optimize this problem in numerics. So I make the simplifying assumption, it's a unique solution, which is somewhat justified in the examples we see because they will always be some kind of symmetry breaking, and or sort of basically if for my optimization, which of those I pick is actually for design not so important, if there are multiple solutions. And then of course I have to handle these constraints. And what I do here is like a poor man's barrier method. So I just use logarithmic barriers to prevent sort of, for example, for inequality constraints, right? So this u of f should be bigger than 0. So my force could also be smaller than the extremal points. It will never be this case because this would be a stupid choice. But yes, in principle they're allowed to. So these are like inequality constraints. And so I have to keep this q away from 0. So use some logarithmic barrier there. And then this is just, okay, this y again depends directly on this f. We have this b, which is basically the chosen set
Yeah,
of...
this is the outmax, so this is something, okay.
Yes.
So psi is the force.
Yes.
It's not the value of the.
No, psi is the force, it's the
Psi
argmax.
is the worst case.
And so yes, and exactly, yes, and then this y is determined by this b of times f, or b is the basis of like load scenarios. F is the three-dimensional vector or low-dimensional vector of weighting of these load scenarios. This is how much my object changes globally, so this elastic cost from before. And then this is, okay, this psi of u is just the argmax of this. And here we assume somewhat that it's unique for like numeric, so it's a simplifying assumption a bit. And then for a leader, we have this J, which is this tracking cost from before, but we also have these constraints that we talked about, that my material cannot be arbitrary, and they again enter through, in this case, like logarithmic variant terms. So I have like lower and upper bounds on my element-wise thickness, given as u minus and u plus, and then I also have a upper bound on the total amount of material I'm spending. And we just enter them by some logarithmic variant terms with some fixed weighting that are chosen by some manual parameter tuning so that it works. And in theory, we could do is you could also do some kind of interior point method where you can change these parameters, but we never pursued this so far. And then again, sort of the cost is the solution is psi of u, the force enters in this tracking type cost we've seen before, where we have this material, and in this case, actually independent of this, you have this the psi of the follower, but again, the follower gets u times some like stochastic distribution, right? So there's some random perturbation happening before the u goes to the follower. And then we have in our case, the leader optimizes the expected value of this outcome. We could also do something else like conditional value at risk or whatever. But yes, we just chose to be simple. We chose here the expected value.
Okay. And maybe one last question is, in the argmax expression, why is it natural to have h of u instead of just identity? Because my understanding is that with this term, you're saying that it's much worse to have displacements in the parts which are supposed to be stiff. Mm-hmm. Whereas if you had dropped the h of u, you just say, okay, the model cannot cheat and say that this point can't move because this point can move because it's not stiff anyway. I don't care.
Okay, so this is like actually the cost of the cost of how much this object is changing internally. So it's also equivalent to how much this object is moving with respect to the exterior force. So if you remember, at this times it's just h to u inverse times m times f, like the forces. So one of them cancels out, and you basically have a measure of cost of the forces. And this is just natural, like elastic object to talk about how much my object is moving. So there is actually here, this measures how much my object is moving. It's just like, so this makes sense in a sense because, okay, maybe I whack. So this is the same as saying how much is my object following my forces. Because as I said in the beginning, my problem is minimize this minus times how much my object following the forces. And because it's a quadratic problem, the solution is unique. And the solution is the one where I have balance between these two. And this is exactly the same cost then here. So I could just easily write y times m times f here. And yes, then there would be no h of u anymore.
Okay.
But this is, so because if you would like go back to non-elasticity, then actually becomes a question of like how do I measure like cost of deformation? Do I measure it by cost of elastic energy, which is written here, or do I measure it by how much it's actually changing everywhere, as I said before? But in this scenario, it's basically equivalent. Okay, and then to optimize this leader problem, we reduce just stochastic gradient descent, which is sort of everyone knows by now thanks to neural networks. And you just every iteration, you choose a bunch of samples from a distribution, so our normal distribution or truncated normal distributions. We compute all the values, we solve the follower problem, and we have some empirical risk. We take a gradient of this and we follow it. And then for the follower problem, what you do is like small dimensional nonlinear problem. And what we do is we just use Newton's method. And you can see that typically for this lower level problem, you converge within like, 10 iterations or maybe 50 iterations of Newton's method, which are very cheap because they are very cheap because yeah, it's small and it's easy to solve. You have some good initialization normally. And then for the outer one, we just do the gradient descent. You can actually see how it goes down. I mean, there's no proof of convergence for this algorithm, but it works very well. But it's pretty expensive because you have to have sufficient samples here. So typically I work with like 128 or 256 samples. That means in every iteration I have to solve this problem like 128 times, the follow-up problem. And I also have to compute the gradient of this distribution follow-up problem. So this is some kind of like shape optimization calculus you have to do. This takes some time. The good thing is you can parallelize this, right? So this is something that's easy to parallelize. You can just do 128 computations parallel if you have enough cores or enough machines you can distribute it. So this is something that we heavily used here. You just put it on a machine with like 128 cores and just do its job.
The fact is that, in fact, to compute, okay, here you compute you need to compute the gradient. It's not something which has.
Yes, we need to compute the gradient. It's phi of u. Yes, it's non-trivial, but you can write it down. So okay, maybe let's say we actually. So I.
No, because it's okay. We could say yeah, that's a big deal. No.
Well, no, yeah, kind of is, but once you get
kind of analysis,
yeah, you have to do you have to like use simplest function theorem to like, get this like the to get the gradient of this, but this is not too hard.
Yeah.
So it's a few lines of calculations you have to do, but it's not too bad. So we don't just autodiff, for example, here. Just like manually calculate the gradient and.
No, it depends. It depends on the shape of your f. You know, yeah. I guess. Yeah, it's come from the fact that you have a handable expression.
Yeah.
Yeah.
But also no.
Yeah.
But also in general, like if you do this game, then basically you just need a Hessian at your minimum of your energy that you're optimizing. It's not too hard to do this kind of solutions or do this kind of derivatives or solution of the problem. There's like by joint calculus or shape position calculus, depending on how you call it. There's like where you previously made to describe it, and basically it's just applying like implicit function theorem in theoretical infinite dimension, but it's finite dimensional, so everything works out. I can show you the formula afterwards. Then I see it's not too hard.
Yeah, I was wondering what do you call convergence here? Because in fact you have a saddle point problem, or I mean.
Okay, yeah. Okay, so convergence is just numerical. There's no proof of anything. So for here, I can assume to converge to a local minimum or local maximum because it's an argmax. This is just worked out fine, and for the other ones also a local minimum.
Okay. What you compute here, J, is the J between U and psi alpha of U, or is it between after each minimum of U?
It's the J after each iteration of my like stochastic gradient descent, and it's relative to the first J because one is just the first in the beginning, and you can see that reaches always some plateau, and the gradient becomes very small of this. So the point is just, okay, it works if you wait long enough. We have no proof that it works, but like, empirically, it always worked out in the end. You just have to wait for some time. And okay, you can also say in the stochastic gradient descent, we actually use line search. We don't do what was done in like neural networks, have to kind of like add them or whatever. That's some like adaptive step size that's actually fixed. But we really do like use line search along the descent direction because we found this works much better in this scenario than doing anything like Adam or whatever.
But yeah, okay, in your stochastic gradient descent, so you say you have the upper level and lower level iteration. So you mean the outer loop, you draw samples, and after you minimize the empirical risk?
Yeah, we draw samples, we compute the empirical risk, we compute the gradient of the empirical risk, and then we take a gradient step in this direction.
No, you're just doing a gradient step.
Yeah.
Just one. Oh yeah, okay.
And then we draw new samples and do everything from scratch again.
But you could take K for one.
Sure. Yes. Yes, you could.
No. I was wondering if you. Okay, so in this is the standard gradient stochastic gradient.
Yes.
So you're choosing.
This is the one from Robinson and Monroe from the 50s. The very basic stochastic gradient descent. And then, maybe you come to some like, examples you can do with this. This is actually my favorite example. So, okay, now we have this roof again, this like simple roof. And here you compare first two things. You compare global tracking loss, where the leader cares about like every point. And this basically means that it has essentially the same loss as the follower problem. Okay, so both leader and follower, one minimizes this, one maximizes this thing, same loss basically. And because, as I said, this is related to each other. And then we see what happens is to build some like reinforcing structures. So what you can see basically some like bars that reinforce the top from the side elements, and also reinforces these corners. So you can maybe to note like the small like triangles here actually in the corner, they are fixed like some boundary conditions, they're just clamped. While then extra it also reinforces it to make it more stiff. And you can see you have some like displacements. Okay, this is always the used material. This is the norm of the displacement, and you can see, okay, you have some displacement area on the top instance. Basically, I mean, but it gives already some like nice reinforcing structures, but this is not really effect. The bilevel optimizations will happen all the time. Interesting it becomes when you start this platform tracking and just say, okay, the leader only cares about the top. And so this has no different loss, because then you can actually maybe first look at this Y and see, okay, actually I have more displacement here suddenly, because actually here the leader doesn't care about displacement, but the displacement in the middle is actually smaller. So here's really more blue and here green. I don't know what you can see this, but pretty closely you can see the difference. And now what happens is, sort of the leader starts to build a fault line to his object. So it starts to build, it makes the object weaker here in the corner. And this means that the follower wants to choose a force, irrespective of where it breaks, that just breaks the object. And so it chooses a force, you can see here, that presses from the left to the right. It presses like on this diagonal. And then this leg in here will just collapse basically, it will tilt down. And this is, of course, has a lot of displacement, as you can see over here. So the follower is very happy, he destroyed the object. But actually the way it tilts down here, because these other material distributions, basically is made up for in the top, and the top barely moves. So basically the leader built something that in German is called a Sollbruchstelle. So it's a thing where your object is supposed to break if something happens, some force comes to it, and so but it's break in a way that still keeps it functional or still is safe in some way. And so this is actually really cool, because now we have also a symmetry breaking effect. So you still have symmetry along this axis, but for example, this axis, the symmetry is not there anymore, which also makes the solution then unique of your follow-up option actually, because there's this clear direction it has to choose. And then you get still some like reinforcement here, but mostly it's here on the top, and you get this removing things in the bottom, but reinforcing the other ones. I think this is a very cool effect you get out of this. And so this effect is somewhat consistent, so independent of how much material I allow my object to have, how much material I give my follower. So we always have this appearance of this position where it should break here in the lower left, and then just it starts to first reinforce more and more the top, and if it has enough material for the top, it starts to build again these beams to the side to reinforce them more and more. But this appearance of this asymmetry is completely, even if I have a lot of material, it's still what happens. So that's a really cool thing to observe. And yes, that's really what I want to say of this problem. So to give a very brief summary, okay, we've taken this stochastic bilevel optimization. We've added some physics to it as an additional level. And in this way, we build a model or optimization technique that can actually be used to do some interesting kind of shape optimization problems where actually have some interesting behavior emerging, this symmetry breaking here, and this creation of these fault lines, for example.
By the way, I assume that what happens during the optimization is that the symmetry breaking happens in the lower level. So I assume that what happens is that, okay, the adversary, so the follower says, I'm going to press there. So then at the upper level, you add stiffness around there. And then it turns around,
so the symmetry breaking actually happens very early in the process. Why happens here? This is, I guess, some kind of numerical noise. I mean, you could imagine there's still some symmetry, right? You could just also break this lower left corner and the upper right one. So at some point, you have to decide which one it breaks. And I think it's just because we assume some uniqueness of the solution of our lower level problem, we just compute one solution. And the one which is chosen in the beginning, I think, determines which kind of symmetry breaking it starts to do, in which directions.
Okay, so actually I hadn't realized, because, okay, it's normal that the forces are symmetric, but U is not symmetric either.
Yes.
Okay.
But if you know the symmetry, you could impose the four others or the three other solutions.
Yeah, maybe yes.
Because you know there is a symmetry.
Yeah, okay, yeah. In the very beginning, I know this is symmetry, like for the very first iteration. But as soon as I change my U, I don't know if this U is symmetric anymore. Because my solution is only my low-level solution is only symmetric, or only multiple solutions because of symmetry. If my geometry is symmetric, and if my U is symmetric, which my material is symmetric, because both of these determine my displacement, and then that's the optimal force.
Yeah, but if after one iteration, your set psi has 4 elements because you know that it must have 4 elements, then it will remain through the iterations. Because you
no, because okay, then it becomes a bit ambiguous, right? So okay, let's assume in the scenario I do my first computation, my material is homogeneous. I have 4 solutions, like all 4 directions here. Then for my leader, actually, these are all equivalent because they take the one with max, right? But all of them will have the same like cost because they're still symmetric. So for them, it doesn't matter which of them. So it will take some maximum. It's not uniquely determined. And then at some point, I have to do some decision here in the optimization, which of these 4 I'm actually going to pursue further, which one I actually assume as the maximum. And then it's just a symmetry breaking here. And although I have to say, I also don't know if this geometry is actually perfectly symmetric. I mean, this is just some like surface mesh that we have given from some design of some pavilion. So it's actually some like almost real world data. So some design that actually been used for something. So there might be already some asymmetries in this mesh. So it might not be perfectly symmetric. So this might also mean why it's consistently always choosing the lower left corner. So maybe it's just slightly different there. I don't know.
That's it.
I have a second project we can talk about if you like, depending on your time. But maybe I give you a brief summary of what I've been doing in the second project because I really like it, and then just a brief overview, and then.
But just maybe you gave first an example that you can make a project with economics and stuff, and how do you relate this kind of example to show on a physical structure when you put some?
Okay. Yeah. What I mean by economics here is that we take like some optimization technique, in this case bilevel optimization, which is like very popular in like economic decision making. Like people, as I said, for example, before, this like law design, or one thing is often like supply chain management, where I have like some like company that wants to build some objects, it has to distribute some kind of thing somewhere, and then there's some cost of transport, my lower level problem, and how do I, at which factory should I produce what, and so on, these kind of scenarios. And then there's traffic optimization. So how do I have like my followers would be like people actually sitting in the cars and driving. They want to minimize the time they get from A to B. And now I have the leader, which basically, for example, they control all the traffic signals in a city. And they want to do something like they want to minimize the carbon dioxide emission or whatever. And so they want to create a control of traffic signals such that the people in the cars make decisions that have some impact on the environment, even though each driver of the car only makes the decision. Assuming they are drivers that don't ignore traffic signals. So okay, maybe that's a strong assumption in some places of the world, but yes.
But how is it with deformation actually?
So it's not directly. I mean, that's the whole point of this, right? So it's just these concrete problems are one thing, but there's like an abstract framework, like an abstract framework of this like nested optimization problems. Also called hierarchical optimization if you have more than 2 levels. And the idea of our question was like, okay, how can we actually use this hierarchical idea in elastic shape optimization, where we can. So there's one like obvious solution where you just take the follower is just physics. And there's something where we want to do one step further, where we have actually like 2 like agents operating like this, 2 engineers in our like mind picture. And so this is something that we did here.
And in this, okay, look, if you need to speak about something else, we should stop here.
No, go ahead. I mean,
No, the fact
I can come back.
I wonder because you show. I think it's really interesting. I wonder. Okay, in fact, it seems that it will depend. You create some kind of very complex environment, and so it's hard to have some kind of feeling about, you know, what is the landscape of the energy you are minimizing, and you know what will be the local minima, what will be a lot of different things. So it's like, you know, you could change your problem and suddenly it's not working anymore, or it's working. Or what do you know about this? Okay, in this work, you have to design what are the criteria to make them working, or it's
no,
you know, the noise you add. Okay, the noise you are adding, and you know the V plus V minus. There is a lot.
Yes, we actually, if you look into the paper, there's like a lot of parameter studies, like how much noise do I add, how much material do I have, etc. And sort of, for example, this effect of the symmetry breaking here was always consistent in like a wide range of parameters, for example. And also maybe let's say this is of course not a realistic like physical simulation that we're doing, right? This is like a very simplified elastic model. And so this is more about like a proof of concept and also more about a design problem than actually a real engineering problem where we really have to compute the things in the end. Because then you have, for example, the parameters that we use here, I once tried to compute, okay, this is actually realistic what we're doing because there is some material parameters in here. And it turns out sort of the parameters we use is basically our roof is made up out of PET, so the plastic bottles, but it's like a half a meter of PET. And the load that we have on the roof is like, I think 6 meters of snow, while there's a like, strong wind on it. So of course, this is not a realistic load scenario in the end, and also not realistic scaling. But yeah, it's just a sort of like a simple type problem. But yeah, but typically it was robust to some change of parameters. So it did not suddenly break completely if you change the parameters. But of course, there's no guarantee. There could be like nasty local minima. If you don't know how the engine exit looks, it's very difficult, of course. There's no guarantee that anything useful or reasonable comes out in the end. But there's a guarantee there is a solution.
And so if you abstract the idea, so what the fact is that you are doing shape optimization, but if you try to explain what the shift you are doing here, if we compare to traditional shape optimization, is that you have this, first you design and you are trying to optimize something which is a second, you have two things. Okay, you have to.
Yeah, we have this.
So how can you?
Okay, so and typically in like elastic shape optimization, what is usually done is you fix one load scenario, so you have one set of forces acting, or maybe you have a small set of load scenarios that you predetermine. Like say, okay, I have 10 different load scenarios I want to be robust against, and then you just take a sort of give all of them a solution, or take just the average of solutions and so on. And here, this is more like a kind of like a worst case scenario that we actually compute the forces, which is very uncommon to do in this kind of context. I will not claim that there's no one doing this because, of course, there's someone doing this somewhere. But at least in this setup and this way of having someone like something in your problem that actually also like maximizes the forces and is able to choose the forces depending on the material is very uncommon. And maybe this is the contribution in this abstract sense to this, and to show that this has some effect. And I would also say there's some in the paper also contribution is maybe there's some like analysis of existence of solution and so on in the paper, but this is much more a specialty of our friends from Essen, so I did not present this here. And also because it does not work, because the proofs break once we make the assumption of the uniqueness of solution, etc. So there's some disconnect to our actual computations.
In fact, you create a shape, and you are making some kind of evaluation of that shape in a given environment, and then you optimize more or less the. Oh, it's okay. It's an interesting thing.
think about that.
Okay, maybe there's a second project that I plan to talk on about, but okay, maybe. But I would just give you like a small teaser of what it's actually about, and then you can decide if I should come like a third time. But it actually would make sense because I'm still working on like a follow-up project to the second project, and then at some point I can talk about both of them in just like one session. And basically what we did here is a surface segmentation, and we created a phase field model to segment the surface into multiple parts for like various reasons. And this has been joint work with, again, my PhD supervisor, Martin Rumpf, and Janosch Meni, who was a master's student in our group. And so basically this is also outcome of his master thesis, and also he did all the computations, created nice images, so I just stole them from him. And sort of the idea here is you want to segment your surface into multiple parts, and there's various reasons why you want to do this. For example, you want to remesh your triangle mesh, you want to use it for collision detections because you want to approximate it by simple elements. You want to use it in multi-resolution methods, which was actually in the beginning our motivation. Or you can also use it for texture mapping in computer graphics. So you have a complex shape. You want to, let's say, complex shape of a cat, and you want to put some texture on that. You want to have fur, so you need to to break it down into pieces and create like textures for each piece, and then map it to the surface. And then similar very related problem is fabrication. You can see one example here. So this is like a spherical lamp you actually buy, and when you buy it, it comes to you in flat pieces. And then you have to assemble these flat pieces to make up a spherical lamp. And for this to happen, of course, the segments that you put on your sphere have to be in a way that you can easily manufacture them from flat pieces. And this is sort of the main, also the main, which is a very similar goal than texture mapping, and the main motivation we've used here. And sort of the starting point was a method called variational surface cutting, where they create a level set method to exactly do this, to compute segments of your surface that can be easily flattened conformally. And conformally means, okay, but just by a scaling of your metric. This means basically some kind of also like simplified elastic model for like sheet metal, for example. And what they did, what one contribution was, they did not explicitly compute this flattening, this mapping to this the 2D space, but they computed the distortion that will happen by something called the Yamabe equation. It gives you like a PDE to compute this distortion you want to minimize. Then our idea was, okay, we would like to do this with phase fields because we like phase fields, and also phase fields have been used in a lot of scenarios, mathematical imaging and material and shape optimization, because they have some like nice advantages. You can easily change topology, and oftentimes like discretizing like the system is straightforward. And like phase fields, why? Because phase fields are like a smooth function on your object or on your space, where basically you have like a smooth transition between -1 to 1, wherever there's an interface. Like one, if I want to segment my surface into two parts, I would say there's a pure element with -1 with one phase, and another phase is one where it's +1, and then you have transition. And but if I want to apply this phase field method to my surface cutting thing here, there comes some upstream challenges. So like topology changing is nice, but I maybe want to have some control of my topology. For example, I want to cut my surface to two connected parts, because I just want to have two parts that I want to assemble at the end, or I want to control the number of parts, let's say. And then, okay, if we want to do multiple segments, what we did here was a hierarchical approach. You first segment your surface in 2 parts, then 4 parts, then 8 parts, and so on. And okay, and another question is, how can we integrate in this framework this distortion thing? And these are some like very nice different challenges that we worked on, and maybe I just focus on one of them, this connectedness thing, because I think this is pretty cool. And maybe it's also related to something we've actually been working on with Alain recently. I realized when I prepared the slides. Because, okay, so how do phase fields work? Phase fields, we have like 2 phases, like a -1 phase and a +1 phase, and a smooth transition in between. And now if I want to say a phase should be connected, I have to do something I want to do something variational that my phases are connected. And for example, here, the simple example, we have like -1 phase, which is actually connected, but this +1 phase is not. And there's like a very tiny transition in between. And then what I do is, and there's an approach by Patrick Dondel, a good friend, that does this in a variational way, where basically what I say is I introduce a modified distance on my geometry that depends on my phase field. That basically says, for example, if I want to talk about the positive phase, that tells me if I have that the distance or the length of a path on my surface only costs me something if I'm in the negative phase. For example, here in this example curve, let's see, my part in the blue phase would be cheap, would be basically free. Then I go through the red phase, and this costs me like a lot, let's say, and then again blue is free. So this is like a modified metric, like modified distance on my object, and this is actually a conformal, almost conformal distortion of my metric, for example, on a surface or on a mesh. And okay, then the distance between 2 points is just like the minimum curve or the minimum length of the curve between these 2 points. And then what I do to make my phase connected is for all pairs of points, I integrate up this distance, but I only care about points where, 2 pairs of points where each of them lie in the positive 1 phase. So this h function will be 0 in this red part, and it will be 1 in this blue part. So, right, so actually I only integrate over my +1 phase. But I don't know actually where it is, so I have to integrate over everything when I restrict myself to the +1 phase. And then for each pair of point in my phase, I look at this distance. And so now if I know if my phase is connected, then I can just take always paths in this blue region, right? Because this blue region is connected. Actually, path connected, but Euclidean space, it's the same thing. So it's connected, so I can find a path in blue phase, so I pay nothing for it. It's for free. But if this is not the case, for example, here, if I want to go from here to here, I have to go through the red phase. I have to pass through the negative phase, so I have to pay for this distance between these 2 connected components. And then if I sort of put a 1 over epsilon scaling on this, and then let epsilon go to 0, it actually becomes a constraint saying, okay, it has to be 0, and it's only 0 if it's connected. And what happens in an optimization case is, okay, if I now minimize this, do some gradient descent, we actually start to build bridges between certain phases, because, okay, the way the gradient of this functional f4 will be localized on this connecting path, and then start to build bridges between phases, and then it will sort of optimize. And I can actually use this to do connected segmentation of surfaces. For example, here we start with some disconnected segmentation where you just follow the fingers separately, and then if you add this connectors constraints for both phases in this scenario, they actually get a connected thing. And then you can also couple this with things such as distortion minimization, and then you can add hierarchical things, and they can actually start to like subdivide like more complicated surfaces like this cow, spot the cow, multiple regions. You can use it for texture mapping in this case. Yes, and then you can also use this for let's see, maybe the hand from the previous beginning slide. So this is the connected thing I showed you before. But if you want to do something that's distortion free, this is a very bad choice. See here, there's a little bit of distortion shown by this texture is like completely distorted. But if I add something that measures distortion, which I will tell you about if you have more time, then you can see that actually cuts the hand or the glove, let's say. Cutting hand is not so nice. It cuts the glove and like the front and the back piece, which are almost flat, and then it gets some nice texture mapping for this. And this is just like a very brief outline what we've done in this project. And yes, this guy come to the end, and maybe we'll talk about this some more another time. Are there any questions, or was the second part clear? Yes.
No, but this last part, so this connectedness constraint,
Yes.
to compute it, it's crazy, because you have to
Yes.
2 points and then
Yes.
So how do you...
Okay, so you have to be smart to compute this, right? So as I said, if I just do this for all pairs of points on my surface or my mesh, it will take forever, right? Okay, so the first thing to realize is I only care about points where this one is big enough, where this one is actually 1. Because my h is between 0 and 1, and it's h where I don't care. It's h in the -1 phase, for example. It's at 0 in the -1 phase. So for these points, I don't care. So I only look at points where this one is actually bigger than 0, and I make it so that this happens only for points I really care about. Okay, this is the first thing, but this is not enough because this could still be like a big phase. But then the crucial part to realize is if I look at, maybe my face is disconnected again. So if I look at this example here, these two things, the distance between any point in here and any point in here will always be the same thing, independent of which points are actually chosen. Because what always happens is we'll go to the closest distance between these two walls, because inside of the wall, the distance is 0. So I can just have an arbitrary path in here, and I only care about the path between, the shortest path between these two. So actually what I do is I first assemble connected components. So I first look at, like, I put all my points, I look at them, and if they're neighboring points and they're in the same phase, they're a connected component. Done. And then I only compute distances between connected components. So this basically then breaks down from, like, I don't know, let's say I have 200,000 points. So I have a lot of comparisons, but normally I have only in the end like 5 connected components, for example, or 2 or 3. And then I just have to compute 2 or 3 times the distance. And then you can, in this case, you can actually just use the Dijkstra's method, like a white Dijkstra on this graph, your mesh, and then this is fairly quick.
But then you have to differentiate because you need to optimize.
Yes.
So,
Okay, but differentiating is not too bad. It's basically backpropagation.
yeah, no, it's, because it looks like you are doing a whole process of finding connected components, and like you said,
Okay,
maybe
so
this a function that you can differentiate. It's maybe not, but maybe it is.
yeah, okay, no. You don't differentiate part where you build the connected components. So actually, your discretization on this part is a bit discontinuous, or like very steeply continuous, because if the component loosens up, it does so smoothly. But we do not differentiate the process of creating these components, connected components. We only actually differentiate the distance between these components. And for this kind of phase field, this works very nicely. If I want to talk about more complicated phase fields, like most Borelli type phase fields, where it's like one-dimensional curves, this becomes much more tricky, which I will also tell you about in another presentation.
But typically, if you minimize this function here, it will just create a short bridge.
Yes, I will do. So if
Like this, it will be like at the very beginning, it will drop.
yes, this is basically, this is exactly what happened if I do like a gradient step or like a few gradient steps. If this is functional, then this would appear, like a bridge would be built here. But typically then this functional will then be 0. So you don't care about this anymore. Well, then this is of course like, if I want to minimize also perimeter of my interface or something, then this will naturally do something else and then just work.